Let's talk about the Newton-Cotes formulas. We start with a theorem. For given positions x0 till xn, so we have a given n as well. If we then find weights which fit to these positions, which fit in which sense, such that for all monomials, this is a monomial, a polynomial is a lot of monomials with some coefficients, such that for all monomials the integration formula is exact. Here, this, if we have such weights, then we can apply the integration formula not only for these monomials, but we can apply this formula for polynomials as well and for arbitrary intervals, not only 0, 1, but whichever a and whichever b. And then in the next step, we will apply that formula also for non-polynomial function. But that is not topic of that video. That will be the topic of the next video. In this video, we will talk about this theorem, we will prove it, and we will have several examples. Okay, so let's go to the proof of that theorem. Okay, now we are in my script. Here the theorem again, which we wrote on the paper. And now we want to prove that theorem. So let's start with an arbitrary polynomial of degree m. And we want to show that if for the monomials this formula is true, then it's also true for polynomials of order m. So that's what we want to prove in the first step, and we will focus in the first step to interval 0, 1, and the second step will be arbitrary interval. So why is that true? Let's start with that sum, this sum here. And instead of p of xk, we can also write that, because that is the polynomial p at the position xk. And when we have that, then we can split this sum. This sum we can split, so we have a lot of sums. And we can reformulate. Let's take that before the sum, so we have that. And then we have omega k times xk to the power of 0. And then the second sum here, that, and again omega k comes from here, this is that, and then this part. So in fact, first we multiplied that parenthesis, and then we reordered that sum, and we get this. Now, because we know that it's correct for all monomials, then we can write as this integral that this is really true, comes from that, and something to the 0th power is 1. So okay, we have that, and this is that, and this is that. And then instead of a lot of integration intervals, we can use only one, and we multiply the a0 into the integral and the a1 into it and am into it, and so we get that. And this is the polynomial p of x. And so in total we showed that this sum is equal to the integral of p of x, and that's what we wanted to show here. So we are done with the first part. The second part is, let's go from the interval 0, 1 to an arbitrary interval a, b. And that's what we do now. Let's say q of x is p of a plus b minus a times x. That means if you request q of 0, then you get p of a plus 0, And if you request q of 1, then you have a plus b minus a, which is b. So, okay, now we can integrate that polynomial q. And what will we use? We will use what we did above. We know that it's exact. We can use the formula and it's exactly integrated. Okay, but q of x is a little reformulated p polynomial. So the antiderivative is the antiderivative of p, but there's the chain rule. So we have to divide by the inner derivative, which is b minus a. And so we are here, and now we can take this factor out. Then we have that, and instead of x is 1 and x is 0, if you use a 1, you get p of b. So instead we can formulate like that. And if you ask for x is 0, then this is a. So instead we can write u is a and write antiderivative of p at the position a. And if you see that, then you know this is this integral with that factor. And instead of using u, you can also use x, and that's what we wanted to have. And then we can multiply this equation by b minus a, and then we get this. This comes from here, and that factor comes from here, and this comes from here. And then the next step, we know that we can integrate exactly this because it's an interval 0, 1, and q is a polynomial of degree m, at most of degree m. And so instead of writing with the integral, we can write as that sum. And what is that sum here? Q of xk is that. And now we proved what we wanted. We can integrate every polynomial of degree m, and we can integrate by evaluating this polynomial at some positions, these positions here, and then multiplying with some weights, summing these values, and then adjust by the length of the integration interval. And that's what we wanted to prove. That's what the theorem stated. The proof is done. Okay. Okay, what do we need next? We need an example. For given positions x0, x1, and x2, let's use n is 2. Okay, give me 3 positions. And let's use the 3 positions. Left is this starting value of the integral. The last one is the endpoint of the interval. And the point in between is exactly the point in between. So let's use these positions. You can also use different positions. It's not necessary that the first point is 0. It's not necessary that the last point is 1. And it's not necessary that it's exactly in between. But this is the natural choice. Okay, if we have chosen that, then we can try to find some weights which satisfy this equation. Okay. And let's use m to be also 2. This is not necessary, as we will later see when doing Gaussian quadrature. But for the moment, the most natural thing is that m is equal to n. Okay. So let's formulate 3 equations. Let's start with j to be 0. And then let's formulate that equation. Here we have x is 0, 2x is 1, x to the 0th power dx is the same as this sum. So omega 0 times x0, and x0 is 0, so times 0 to the 0th power plus omega 1 times next position, so it's a half to the 0th power plus omega 2 times the last position to the 0th power. So what is something to the power of 0? Something to the power of 0, this is 1. This is also 1. And this is an interesting point because 0 to the 0th power is mathematically not well defined. In this case, 1 is the right choice. So it's the constant 1 function. So we have here also a 1. Okay, now let's think about what we have here. We integrate from 0 to 1 the constant 1 function. So here we have a 1. And here we have omega 0 plus omega 1 plus omega 2, and each weight is multiplied by 1. And this is our first equation, equation number 1. Now let's go to j to be 1. Then we have x from 0 to 1, x to the first power, so we have x, and then omega 0 times x0, the first position, to the first power, plus omega 1 times second position, a half, to the first power, plus omega 2 times the last position to the first power. And so we get the equation. What is that integral value? The antiderivative is x squared divided by 2. X squared divided by 2 at position 1 is a half minus 0. So here we get 1/2. And then here we have 0 to the first power is 0 plus a half times omega 1 plus 1 times omega 2. And this is our second equation. Then let's go to j to be 2. Let's integrate here x to the second power. Dx is omega 0 times first position to the second power plus omega 1 second position to the second power plus weight 2 times 1 to the second power. What do we have here? Antiderivative is x cubed divided by 3. At the position 1 is 1 divided by 3 minus 0. So we have 1 divided by 3. And here we have 0 times omega 0 plus a quarter times omega 1 plus 1 times omega 2. And this is our third equation. And what do we have here? We have 3 equations for 3 unknowns. Okay. And which kind of equation? What are the unknowns? Omega 0, omega 1, and omega 2. And we have a linear equation, linear as well. So we have a system of 3 linear equations for 3 unknowns. Okay, so we can reformulate. And we can reformulate like that. 1 is equal to 1, 1, 1. This multiplied by that is that. So this is our first equation. The second equation, a half. And here we have 0, a half, and 1. And third equation, a third, 0, a quarter, and 1. Okay, we have this linear system, and now you can solve that system. For example, this line minus 2 times that line, and then you will get omega 2, and then with the help of that line you get omega 1, and if you have omega 1 and omega 2, then out of this equation you get omega 0. Do that by your own. The solution is, I did that by my own. It's 1 divided by 6, it's 4 divided by 6, which is 2 divided by 3, and it's 1 divided by 6. This is the solution. Having the solution, you can easily check. 1 times that plus 1 times that plus 1 times that is 6 divided by 6. It's indeed 1. a half times that is 2 divided by 6 plus 1 divided by 6 is 3 divided by 6, so a half. And a quarter is 1 divided by 6 plus 1 divided by 6 is 2 divided by 6, so it's 1 divided by 3. So indeed, this is the solution of that system. So with this choice of omega 0, omega 1, and omega 2, these three equations are satisfied, and that means that these three equations are satisfied. And then we are in the situation of that if, yes, it is, then we can do that for all polynomials. So let's go to the then part. Give me some polynomial, we will check, or we will apply for that polynomial. For which shall we apply that? Okay, please give me some polynomial of degree 2. Maybe you give me 2 times x squared minus 3 times x plus 4. You can use whichever coefficients you want. I have chosen this one. And give me some arbitrary interval, whichever you want, not 0, 1. It can be 0, 1, but maybe more interesting would be another interval. Okay. Maybe you give me 2, 5. And then we can integrate without integration. So if you are interested in this integral value, then you can apply that formula and 100% sure it will be this value. You can do that also by the antiderivative and then value at position 5 of the antiderivative minus value of that antiderivative at position 2. And that's the normal way to calculate this integral value. But you don't need to do that. You have an alternative, and this is that. So b minus a, 5 minus 2 times, and then apply that. First weight is 1 divided by 6. The value p of at position a plus b minus a times xk. So maybe we need a picture. These are the positions here. And then we transform these positions x0, x1, and x2 to new positions. And that's the following you do. This is our integration interval here. And then we adapt to this integration interval. And then we have that way. And that in between means also take the value exactly in between. And that is 3.5. You can get to 3.5 and 5 also by applying that, but that's what is behind that. So it's p of 2 plus 4 divided by 6, the second weight, times p of 3.5 plus 1 divided by 6 times p at the position 5. And what do we get? So we have 3 times 1 divided by 6. Evaluate your polynomial at position 2. 8 minus 6 plus 4 is a 6. Plus 4 divided by 6. Evaluate at position 3.5. Maybe use electronic help. 3.5 squared. Okay, that's not so nice. If you do it correct, then you get an 18. Plus 1 divided by 6. Value at position 5, 25, 50 minus 15, so 35 plus 4, so 39. And if you multiply, here you get a 1, here you get a 12, and here you get a 6.5. And 1 and 12 is 13, and 6.5 is 19.5. 19.5 times 3 is 58.5. And if you calculate that by using the antiderivative, you will also get 58.5. So we integrated without integrating, but only by evaluating. So this was our first example. What did we do in the last video? There we did the Simpson formula. This is also a formula which does evaluate for this problem at position 2, 3.5 and 5. And let's check if it's the same or if there are some differences. What is Simpson? Maybe you remember. And the formula was the integral value is approximately for arbitrary functions and exactly for polynomials of degree 2. So equal in this case h times a third times y0 plus 4 divided by 3 times y1 plus 1 divided by 3 times y2. And in the first moment it seems to be a different kind of thing, but let's do that for that example. In our example this is position 2, 3.5 and 5. And so in between this is the h, this is 1.5, 1.5, 1.5 you can also write as 3 divided by 2. And then a third times, what is that y value? That is the value of the function. In our case we want to compare applying for this function. So this is the value at position 2 plus 4 divided by 3. Then this is the value for position 3.5 plus a third times value at position 5. And now, is that the same or not? Yes, it is. Maybe you see it. 3 multiply the half inside here, and then you get 1 divided by 6 times p of 2 plus 4 divided by 6. And so applying Simpson is exactly what we did here. So that means Newton-Cotes is the more general thing. For n is 2, then we get Simpson. For n is 1, we would get the trapezoidal rule, and for larger n, we get something new. Okay, but maybe you remember last time we found these weights by a complicated calculation. Now we have a more structured way of finding these weights, so life becomes easier to do that job, and so life will become more easy if we do that not only for n is 2 but for larger n. So we have a better way to find the weights. Please keep in mind we have 2 steps. First, find the weights, but finding the weights has to be done only once in mankind's history. And if we have the weights, then we can apply. So finding the weights is more easy. If we have the weights, then we can apply. And applying it, Simpson and Newton-Cotes is the same. And now let's do that. Let's find the weights. Let's find the tabular. First, we have to choose the positions. And what is the most natural thing? If we are on the interval 0, 1, let's use the first point to be the left 0. Let's use the last point to be the right endpoint 1. And let's use all the other values linearly spaced. All distances are the same. That's the most natural thing. So let's choose an n, and then let's choose the most natural choice, and this is 0 is the first, 1 is the last position, and then linearly spaced. And so this is 1 divided by n, 2 divided by n, 3 divided by n, 4 divided by n, and n minus 1 divided by n. This is our choice. Then we formulate that equation. And if you do that, then you will find out we can directly write here. First line is always consists only of ones. The second line, what is that? This is that structure. So we can write x0 to the first power, x1 to the first power, and xn to the first power. Then the next line, x0 to the second power, second power, second power, and the last line always x0 in that column to the nth power, in that column always x1 to the nth power, and in the last column always xn to the nth power, times our weights which we want to find. It's clear these are numbers. If you have chosen n, these are numbers, all numbers, no x. But here we have the unknowns, omega 0 to omega n. And on the right hand side, this is 1, first line always 1, doesn't matter which n you choose. Then a half, second line, a third in the third line, 1 divided by k. So in the last line, 1 divided by n minus 0. Okay, so you have that system. And then we will use electronic help to get the solution. The best is use a computer algebra system. To solve the system of linear equations, I use this abbreviation. Okay, and if we do, we get a tabular which I have in my script and which I don't want to write on that paper. And here is that tabular. Let's run that code for n to be 1. Let's check if we get this trapezoidal rule. I don't want to show you my program because I want you to do that by yourself. Okay, so let's run. In this case, the matrix looks like that, 1, 1, 0, 1. The right hand side is 1.5, and the solution is a half, and that's what we have here. Okay, then let's run that code for n is 2. And then we have that matrix, we had that on our paper, we have that right hand side, and then we get that answer. We prefer that as a fraction, so we can do that dirty trick. And so we see omega is 1 divided by 6, 2 divided by 3, what is 4 divided by 6 here, and 1 divided by 6. So we reproduced that line. This is a dirty trick. We cannot be 100% sure that it's really these fractions, but it's true. So I don't want to call the computer algebra system in that video, but I did that by my own. So let's run the code also for n is 3. In this case, our matrix looks like that. The right hand side looks like that. And the answer looks like that. In fractions, it's 1 divided by 8, 3 divided by 8, and 1 divided by 8. So we have that line. So let's run the code for n is 4. And we see it's 7 divided by 90, 32 divided by 90, but we see 16 divided by 45. Okay, this is 32 divided by 90. Then here expand that fraction with a factor 6. Then you get 12 divided by 90 and 32 divided by 90 and 7 divided by 90. Let's run the code for 5. And we get that tabular, and now it's not very much fun to compare that with that. And so I wrote some code to do that comparison. Here I entered this answer, 7 divided by 90, 16 divided by 45, 2 divided by 15, 16 divided by 45, and 7 divided by 90. These are the nominators, and 90 was the denominator. And I want to expand to the denominator 90. And here, with the help of that code, in the end, I will get... What do I get? I get the expanded version to denominator 90, and we have these numbers 7, 32, 12, 32, and 7, and that's what we have here. Now our code with 5 gave the answer this, and now let's compare these with the common denominator 288. Let's write these numbers. 9 divided by 288, 25 divided by 96, and the rest of the numbers are equal ones, so we can stop here. I want the denominator 288. Let's run the code. And I get 9. No, it was a 19. 19, 75, 50, 50, 75, 19. Okay. Okay, let's run the code for 6. And we get that 41 divided by 840, 9 divided by 35. So again, let's go to the denominator. Let's run, and we get 41, 216, 27, 272, and then these numbers again. Now let's run the code for 7. And then we get these fractions, and now these are not identical to this line. Why is that? Because we use the dirty trick format red, and so MATLAB Octave does not use rationals to do the calculations, but in the end this number here is transformed to some rational, and Octave MATLAB tries to use not too high denominators. So if you use format rational and I show you pi, then you see pi is 355 divided by 113, and that is not really true. Pi is not a fraction, but it's the rational in that situation, which is displayed because this rational is close to pi. So pi and 355 divided by, it's close together, but not completely equal. As you can see here, it's correct up to that digit, but from then on it's not equal. And that's what MATLAB and what Octave does when saying format rational. So in this case, we will need something different, and what is more easy than to check what is in Wikipedia. Okay, this is the German version of Wikipedia, and there in the end we have also a tabular, this one, and these are the weights till degree 10. Funny thing, in the English version of Wikipedia, this tabular is not included. I think it would be a good idea to include that. And here we have the answer for n is 751 divided by 17,280. And here we have also the version with the reduced fractions. And if you do everything right, then you will get that tabular till degree 8. And here also we have a line 9 and 10. I did not want to include that into my script. Okay, we have this tabular. This tabular has to be done only once in life, once in history of mankind. But we are at the university, so we want to know how does these formulas come into life, and that we did in every detail. Okay, and here in my script, one more remark. 0 to the 0th power is not defined normally in mathematics. If we ask MATLAB or Octave 0 to the 0th power, it gives me a 1. This is not really true. Why? If you have 0 to the power of something, let's say this something is b and b is some number, then the answer is 0. For all b's larger than 0. And then the natural choice is, so if here, this is the b line, 0 to the power of b is a constant 0, so the natural choice would be that 0 is the answer. So 0 to the 0th power should be 0, otherwise here we have a strange situation. So the natural answer to 0 to the 0th power is 0. But if you have something to the 0th power, then you get always 1. And that is true for all a's on the line only it's not clear if we have a 0 to the 0. So it's always 1. So the natural choice 0 to the 0th power is a 1. So in this case we get 0 to the 0th power should be 1. And so we have two natural choices, and 0 is not the same as 1. So often for electronic calculators you get an error. You get an error if you ask for 0 to the 0th power. And for example, WX maxima, it's a computer algebra system, it will return an error if you try. But in MATLAB, 0 to the power of 0, 1 is returned. And in our context, this is exactly what we want. If we say, okay, we want to be correct, mathematically completely correct, then we have to say here, if x0 is 0, and it's in our context always, then you have to use a 1 instead. Then I cannot write that way. Okay, that's for the experts of us and all mathematicians of us. I want to say that. Okay, so that's great. And then one last thing, we can also state the same theorem as we did above, but instead of saying here a 0, 1 and then this, here this would be a 1, we can also state like that, and then this is also true. It's a little more general formulation we did not need in this video. We will need a little later, maybe we will need, but for the moment this is completely of no interest. So if you want, skip that theorem and only remember, okay, it's a little more general than the above theorem, but we did not need so far, and maybe we will never need. So this was our video about the Newton-Cotes formulas, and in the next video we will talk about that, how to apply for arbitrary functions, non-polynomials only. That is really interesting, and we will see that is a quite easy thing.